Hello again to another Agakala React, and today we will be watching why is there absolute zero temperature? Why is there a limit? And I have no idea, so let's just learn. Oh, I'm actually cold, so I'm talking. And this is from Day After Tomorrow, isn't it? Oh my god, it's so cold in here!
The highest temperature scientists obtained at the Large Hadron Collider is 5 trillion Kelvin. The lowest temperature that people managed to obtain is 0.00000000038 picokelvin, or minus 273.14 degrees Celsius, or minus 459.66 degrees Fahrenheit. But is there anything else hotter or colder? What does colder or hotter mean? Why are some objects warmer than others? What is absolute zero? And why is it minus 459.67 Fahrenheit and minus 273.15 Celsius? Keep watching to learn from this video. Absolute zero. Energy is the foundation of the universe and the basis of everything. It permeates everything that exists and sets in motion all the mechanisms of the universe. Energy takes on different forms and manifests itself differently in the movement of objects, chemical reactions, and basic natural phenomena. According to the world's most famous formula, E equals mc squared, even matter itself is just a form of energy, and in the matter, energy acquires the most obvious form for us: temperature. Living beings feel the temperature of everything by registering how much the substance is heated, and they feel very well having a shower. We can easily distinguish when the water temperature changes, even by a couple of degrees. But after all, both hot and cold water consists of the same atoms. Then what lies at the basis of such a phenomenon as temperature? It's all about the movement of atoms. They are always on the move. Every molecule oscillates even in a fixed piece of iron. Yes, even when trapped in a crystalline structure. From a school physics course, you probably remember that the body's kinetic energy sets it in motion. It is the measure of this very movement of molecules, and the higher this energy, the faster the atoms move. This is what determines the temperature. Body temperature is closely related to molecules' average kinetic energy. The higher the temperature of the body, the greater the average kinetic energy of its molecules. We can easily imagine what happens when the kinetic energy of molecules in a piece of iron or ice continues to increase. They will oscillate faster and faster, and at a certain moment start pulling away from their neighbors and striking out on their own, almost literally going into free floating. Because that is how a solid turns into a liquid. Ice melts and metal melts. Okay. But now we already know all this. But in the past, it was hard for people to comprehend these phenomena, just like everything else in nature. How did people come up with the idea that the temperature can be measured? Have you ever thought about why it's easier to raise the temperature than lower it? Can you heat water to 100 degrees without a kettle?
That's a good question.
Piece of cake. And Boy Scouts can do it without matches. Similarly, one can easily turn ice into water and steam, but try to cool the same water by at least 10 degrees without a refrigerator, let alone turn it into ice. Just think about how you would do it. Not a clue? Well, that's precisely the point. Humanity learned how to obtain low temperatures only in the last 100 years, at the recent stage of scientific and complex technical advancements. Any idea why? And why do we operate with only positive values when measuring length, mass, and time, but apply some negative values when it comes to temperature? After all, you see, a distance of -5 meters or a weight of -100 kilograms sounds too abstract and very impractical. Only the temperature has both positive and negative values. And this doesn't confuse us at all. What's the deal here? Let us remind you how people began to measure temperature. In 1714, the self-taught German physicist Gabriel Fahrenheit set the lowest point of the temperature scale. He took the temperature of melting a mixture of ice, water, and ammonia as 0. It was the lowest temperature known to science at the end of the 17th century. As Fahrenheit claimed, he took the normal temperature of the human body as the second reference point. He divided the interval between these 2 points into 100 equal parts, which later became known as the degree Fahrenheit. On the Fahrenheit scale, the melting point of ice is +32 degrees, and the boiling point of water is +212 degrees. This is the scale we still use in the UK and the US, and the Celsius scale is more familiar to the rest of the world. The Swedish astronomer and physicist Anders Celsius proposed his scale in 1742. He came up with a simple...
I need to check that because it's kind of like annoys me a little bit about that we still use it in UK. I don't live in UK, but I'm pretty sure they don't use that Fahrenheit. They might use it every now and then, but... the UK doesn't use Fahrenheit like the video claims. We use Celsius and centigrade. For some reason, during summer TV weather forecasters like to also tell you what a hot day in Fahrenheit too. We have no idea why though. I live and grew up in the UK and essentially never use Fahrenheit. My oven dial is in Celsius, weather forecast primarily. The other thing about Fahrenheit, well, I heard that he was born in one country that is very dear to my heart. So, Daniel Gabriel Fahrenheit. Yeah, he was born in Gdańsk and died in Hague. So, what's the story there? Born in Poland to a family of German extraction. Okay, I get it. Yeah, born. It can be. Okay. Because I seen somewhere saying that he was Polish, and I'm like, really kind of strange. I never heard about it. I never was thought about it. Because honestly, this is something. He is obviously well-known scientist. So why never? Again,
and most obvious framework. Freezing water, 0. Boiling water,
100. Yeah, there you go.
That's all.
Easy,
simple,
peasy, Japanesey.
And each of the 100 divisions in between became a degree Celsius. You've probably already guessed that the Fahrenheit or Celsius scales that we all use are intended for purely domestic purposes and are quite far from the scientific definitions of temperature. That's why negative values are purely conventional. In fact, there exist no negative temperature values at all. But 0 temperature is quite a real thing, or so it seems. This fundamental unit of measurement is like the speed of light. With enormous efforts, you can get close to it, but there's no way that you can reach it. Otherwise, something bad would happen. If you keep in mind the start of this video, then you probably remember that the temperature is directly related to the movement of speed, or rather, the vibrations of molecules. The slower the oscillation, the lower the temperature. Logically, there exists a certain temperature point when the movement stops altogether, and this is precisely absolute 0. But why can't we reach it? What for is a whole different question altogether, but never mind. Suppose the molecules will stop. So what? In fact, this is where it becomes much more interesting. But the answer is a little creepy. In 1802, the French chemist and physicist Joseph Guy Lussac discovered that the volume of a gas at a constant pressure changes in direct proportion to the change in temperature. Moreover, whenever the temperature of the gas changes by 1 degree Celsius, its volume changes accordingly by 1/273 of its volume at 0 degrees Celsius. And this applies to any gas regardless of its nature. You don't need to have a wild imagination to follow a linear relationship. It turns out that when the gas is cooled to -273 degrees Celsius, it should simply disappear.
How did they do that though?
If Guy Lussac had been a little more superstitious, he would certainly have been too afraid to touch something otherworldly. A terrible secret that was always there. But he was a scientist and came to a different conclusion, that the temperature of -273 degrees Celsius is the lowest. It's a theoretical limit. Absolute zero temperature. And it was the right
theoretical,
conclusion.
huh?
From this conclusion there comes the scale of absolute temperature,
Kelvin?
otherwise
Oh,
known
yeah.
as the Kelvin scale. One that doesn't have any negative values. And it is this scale that is used in science. And its zero is equal to the real absolute zero. But some questions remain unanswered. What is the nature of this absolute zero? To be more precise, absolute zero corresponds to a temperature of -273.15 degrees on the Celsius scale and -459.67 degrees on the Fahrenheit scale.
I was just thinking that there was no answer for, or there was very little of them, and it's just so yeah. So I was taught about the Kelvin scale, probably because it goes from zero as an absolute zero, and then up to the 273, isn't it? And then obviously Celsius, because that's what we're using in Poland. I was told of Fahrenheit just as a kind of like a novelty, I guess, because it's not something we were using. But you can hear about it in the movies from America and all, on TV, so probably that's why. And some other, like, just kind of like a novelty things. There's another one, there's another scale for temperatures out there, but I can't remember what is it. And yeah, pretty much all. So now I'm kind of curious, did they actually measure, did they got to them that 0 Kelvin, or is it just like you mentioned, that theoretical when that French guy said?
Why would all atoms stop at this temperature? Why precisely at 273.15 degrees? This question is essentially philosophical. This
so
is
it is,
the way
okay.
things are in our universe. Like the speed of a light or the mass of an electron, or anything that couldn't be analyzed any further. What happens to the substance when its temperature begins to approach this critical point is much more interesting to us. Earlier in the video, we already found out that as the temperature rises, the atoms exceedingly accelerate and then take off, turning a solid matter into a liquid. This continues to happen as the temperature rises. Even in a liquid state, the substance becomes too constricted and turns into steam, and then even into plasma, a rather strange but spectacular form of matter. But what if we conduct a reverse experiment and start lowering the temperature? The molecules of the cooled gas will begin to slow down, which would trigger the process of condensation. The gas turns into a liquid, which then solidifies and becomes a solid. Its molecules are well organized, but they still oscillate. Further cooling of the solid will cause this oscillation to become less and less noticeable until it almost completely stops. The key word is almost. A complete stop is impossible, otherwise something bad that we've mentioned before would have happened. We can only guess and speculate what it might be. But in any case, we would be wrong, since this is actually impossible. Even without reaching absolute zero, but only when approaching it, The substance literally begins to work magic, something that defies the usual laws of physics. Exploring the properties of metals during deep cooling, scientists discovered an amazing phenomenon. Some metals almost completely lose their electrical resistance at a temperature close to absolute zero. They become ideal conductors, capable of passing a current through a closed circuit for a long time without the source of electricity itself. The phenomenon was called superconductivity. On their way to absolute zero, some gases show other miracles. For example, helium becomes liquid at minus 269 degrees Celsius. With a further decrease in temperature, its atoms can leak through microscopic capillaries without friction. In the substance's normal state, this is also impossible. This phenomenon was called superfluidity. Finally, ultra-low temperatures allowed scientists to discover an additional fifth aggregate state of matter. You might wonder, what else can it be besides a solid, liquid, gas and plasma? It turns out there can be other states which make us one step closer to the very miracles of quantum mechanics, which are almost like magic. The existence of this matter was predicted by Albert Einstein back in 1925 based on the work of the Indian physicist Bose. For the first time, its potential existence was experimentally confirmed by Eric Cornell and Carl Wieman in 1995 at the Joint Institute for Laboratory Astrophysics, JILA. To obtain this substance, scientists use gas from rubidium atoms cooled almost to absolute zero. But what is so special about this substance that they were trying to obtain it for 70 long years? This is something strange that is difficult to understand, let alone explain. In simple terms, we can say that some well-known quantum effects occur in the Bose-Einstein condensate, such as superposition, when a particle is in several different places at the same time. Yes, these oddities of quantum mechanics have puzzled scientists for over 100 years. But at least this was about elusive quanta, and here we are talking about the macro level where we can almost see all the wonders of the quantum mechanics through a microscope. In the lab, scientists have already learned how to experimentally slow down light using the Bose-Einstein condensate, and not by thousandths, but up to an incredible 0.2 millimeters per second. Would you believe this? It's too early to predict how this fantastic state of matter could benefit humanity. Just like this, the first researchers of electricity could hardly even imagine what their findings would turn into in a matter of decades. Nature is paradoxical. The tiniest particles of the very fabric of the universe give physicists answers to the biggest questions. Who knows, perhaps the current breakthroughs in the field of absolute zero will someday lead humanity to absolute infinity.
You never know, it could be. Yeah. That could be, we're gonna... did I forgot to put the... I did. Okay, great. Okay, gonna have to figure this out later. Anyway. That was really interesting. So there is no way of actually reaching absolute zero. I never realized that. I learned something new. I thought that I actually did reach that for some reason, and I don't know why I was thinking that. It just shows me that physics is not my strength. Anyway, thank you very much for watching, and I'll see you tomorrow. Bye!